So some main thing first, probably you would already know that as promised, I upload the assignment 2 already because it officially released by the end of this class, right? So because we cover all the material today, and tentatively I give you 2 weeks to do it, but I will ask you during the break if you might need more than that 2 weeks, you need 1 more week, okay? But tentatively will be 13th. But if you need more, then we will figure that out how to get that more. But at the moment, you can tell me whether this is sufficient or not, okay? Because this is the last assignment, only 2 assignments for our class. So without further ado, let's finish lesson 6 today. And since we will finish lesson 6, then we would have another quiz. Question 6. Okay, because every 2 chapters we have a quiz. Okay, it can be next week or the week after. So you can decide by that. Okay. Now let us continue our journey on lesson 6. I will see if we need to spend a lot of time on LISO or we just quickly boop and over. Okay. So let's see. So let us briefly review what we have covered last class. For prediction, it simply means that we are not interested in looking the regression coefficient are different from 0 or not. We just care about how it predicts. So that's why you don't talk about hypothesis testing. You don't talk about estimation. There's nothing. It's a prediction error. Same as most of the machine learning technique you study in the class. So we are not interested from this topic is we don't care about coefficient of different 0 or not. Okay, so that is a slightly different. But what does that mean? It means the model by itself is only useful for prediction. Okay, it doesn't tell you anything if one coefficient is larger than others. It's just in terms of explaining, say, if you want to have a loss function of mean square error, then that is the model that minimizes that. Okay, it doesn't have anything to say further. Okay, and the X is the bunch of things have many names, input covariate features, and Y is the predict. And just to recall what's different between classification, probability, and quantitative. We focus on the quantitative one. So we predict the actual value of Y. And you learn from the other class, like logistic regression, you predict probability, right? And the main difference between the two would be this would restrict your Y from 0 to 1. If you do this, Y can be beyond 1 or below 0. So, but if you ask me, do they perform very differently? The answer generally is no. But you have a difficulty to explain to your boss, your model predicted probability is 1.3, right? But in general, these two would not be too much different. At least for the data not too far away from your model. And classification is to force us to say 1 or 0, right? But this is you learn in the machine learning class, so I'm not going to overlap, right? Otherwise, you would complain overlapping too much, okay? I mean, that has been the case, right? Because that's why I try not to cover anything that overlap with them. So I'm hesitated to talk anything about LISO. But in the assignment, I have a LISO, so I seems an obligation to at least cover a little bit. But if you think it's too overlapping, then I just go through it quickly. Okay. Sorry. So since we care about prediction, so we have to know how to do predict, right? And the main thing is look at the prediction error, which is the thing you predict and the model. So the data you have, right? It's your model minus your data. Of course, you can do the other way around. Doesn't really matter. And this part, the error, will consist of 3 things, right? One's a bias, one's model error, one's general error, right? And I'm not going to elaborate. I think the machine learning class have already talked with this in very great detail. So, but if you do have questions to ask me, because we covered last class already. In particular, we focus on the quadratic square loss function, right? Square loss function, because it's symmetric, it's always positive. So also, the larger the error, you punish more. So this is all a very nice feature, right? But those of you who don't like this may consider absolute value, which also okay. But in general, we focus on square because of the mathematical beauty they get. But because of now we are using computer anyway, so doesn't really matter that much. So this is the average error, right? Because this is the error, right? So this is the average loss, right? Because loss is defined as square. So it's average loss is the MSE, and square of average loss is RMSE. And you would ask, would it be same if I minimize this guy, or minimize the SSE? Yeah, they're all the same. But in terms of performance in the computer, RMSE works better because the magnitude are square root, so everything will scale down nicely. Okay. And although we don't go to the model in math, but always when we look at different model in machine learning or regression, there's always trade-off between the two things, bias and variance. Okay. And there's if you increase one, you reduce the other. So there's always a problem is if you estimate a more complicated error, you're likely to introduce more bias, right? Because it may not, the assumption may not fit the world, so you make a miss. Okay. But if you make a complicated model, usually you reduce variance. So that's how the thing trade off. So the more complicated model, likely you have more bias, but you have less variance. The most simple model, likely you have less bias, but you have high variance. Okay. So I think you learned that in your machine learning class already. So I'm not going to elaborate because if you look at any machine learning class, it's a chapter 1. Okay, pick up the standard textbook, machine learning. But anyway, I mean, it's not in our class anyway, so I just put it there in case you're interested in that. What we want is, since I was told, right, when we taught the part-time class, I was told that students would like to see more application. So that's why I decided the course is application driven by Python. Of course, if you don't like that, you can let me know. Next time I can teach more, I mean, theory for your next cohort, not for you guys, but next cohort, enjoy or suffer. So the idea is, it is a very practical question. If you want to sell a car, what price you want to sell, right? Suppose you want to sell a second-hand car or second-hand house. what should be the price, right? Of course, you get house property, you go to central line website or any website, they'll come up with a price, right? But you may ask, can you come up with your own, right? Because you want to know. And the idea is very simple, right? Look at what what price is being sold in current market and can predict. The difficulties of the car market is because car have come with different quantity and different characteristic. So that means that it's very hard to figure the price if the market is not thick enough. Okay? If you have many cars being sold, then you don't have too much trouble. You can one simple regression, you are done. But because of the data, you have to be very careful. Just remember what is this data set, your prices, where the car being listed, how good is a car, right? When is it, the condition, how many miles are being driven, and type of the cars, what kind of cylinder, what kind of drive, what kind of fuel, what kind of type, and whether the dealer is selling the car or just the owner selling the car, right? Because dealer are usually more aggressive. So we do it last time. We focus on Chicago, and we drop a lot of data because when you try to look at data, these are data lack of observation, so we drop them. Okay, and you also filter out something is unrealistic because remember data is scrapped from the web, so it can have some error. So you have to be very careful how to do it. I mean, this is something that I think you also learned from other class as well. So you have to clean the data out, right? Because this also fit the first class we said, garbage in, garbage out. You want to do especially prediction. If you want to do the right prediction, you have to clean things out. So I think we did that last time carefully, this part, and I'm not going to quickly go again. So Panda, NumPy, our friend, right? This is Dino data. And this is, we filter the data, right? According to what we have said. And this is to drop unrealistic data. And this is trying to change the verbal variable, which is excellent, good, and new, to dummy variable, which is 0 or 1, right? If the excellent will be 1, then it's 0. So this is helping on one regression, right? This is called dummy variable, and in prediction, it's called encoding the data. Sorry. And this changed to number of cylinder, either 6 or 4, right? And once we did that, we know age and the price usually not linear, so quadratic. So you add a square term and cubic term. Of course, you can go fourth or fifth, up to you. Okay. And same for odometer, you can also do the cubic. Doesn't really matter. But here I just do square, for in the book. You can do cubic, doesn't really matter anyway. And here is 5 regression. So for prediction model, usually you have a lot more than 5. You have many of them. And then at the end, you pick up the winner. So it's a horse racing game, right? Because you're not looking at the internal mechanics. Rather, you look at which one would make your loss function the lowest, okay? Because you don't actually care, is this make more sense or this make more sense, right? You would try to first round look at which one is better predictor. And then at the end of the day, if they're so similar, then you use your domain knowledge to pick the one, right? So that is slightly reverse than dot one regression, right? Usually regression would be reverse. Use domain knowledge to pick what should be there. And once you do that, you pick which functional form fit better, right? That's we do the hotel price and distance, right? With no hotel and the hotel price and distance, right? This is the thing that relates, and we look at which format to do and pick the best one. Here's reverse, okay? Because why? Because usually we will have huge number of predictors, especially like this case. Then you can't really pick up the right one. Of course, you can do it, but in terms of prediction, your goal is prediction, right? Rather than explain. Okay, so that's why you would first see how it works. If you can't design, you use domain knowledge. So you will see I have 5 different model, but you can have as many as you want. Okay. And this model is just a string, it's a text. So here equal to something doesn't mean you run the model. It just mean bunch of text. Okay. And the snake means equal sign y equal to this plus this, so on and so forth. Right. The first one is just explain based on age, right? Age and also how long you've driven, and so on and so forth. I think these are the model that we find. And at the end, last line is trying to put all the model string into a list. You can loop over that because we're going to do everyone, right? Of course, I only show 5. When you actually do your project, you can do more or actually put in practice. And then our old friends, that model formula API is for running regression. Okay, you would do is you would initiate an initial list where you put your result there. Okay, and you loop over every equation in that list. You run the regression. Okay, it's a pen, so basically you run this regression. Okay, and I use XC1. You can use X3. Doesn't really matter because we're not doing prediction. So whether covariance doesn't really matter because we're not checking any SD. Okay, so whether you use XC1, XC2, XC3, XC0 doesn't really matter anyway. And then you feed the data, right? Run the regression. Once the regression, you put the result in the list. You run all 5 equations. So this will contain 5 regression results there. Okay. And here is the star glazer, which I showed in the previous chapter, which is trying to show all the regression because of the PowerPoint page limit I just told you for. You can do 5 in the Python code. So here is the model. You will see a lot of this thing, a lot of stars. Of course, you want to look at star if you want to do regression, right? You want to say, oh, this is relevant, this is not relevant, this is relevant. If not relevant, probably won't take it out, right? But remember, what we're doing is doing prediction. So the star to us mean very little, right? What is needed for this set of regression, we care about the R square, right? And we may also care about the residual standard error, but R square is the thing that we would like to see. And you see the R square in this model is pretty good, right? 80%, 89, 91, 91, 92, right? So look at the prices. Simply look at the age. It's already explaining 84%. So just age is the single most important predictor in the car price, right? And then if you incorporate more, then you go to 91, right? So basically, this model pretty good, right? In terms of based on data, okay? In sample is pretty good. Out sample, I don't know yet, but we'll take a look on those. But at least you know this is a good model. And some of you would say, okay, why look at R square? So that R adjust? Yes, you should look at R adjust because you use a different model. So you should punish, you use more regressor. In that case, doesn't really change a lot. So it's comforting to see if I'm going to use this model, I would just simply use the last model, right? Because already discount the number of regressor. So I will use this model, which fit almost 92%. Is that okay? So this is something we covered last time. And Once I do that, because remember our original goal is to say what should be the price, right? To be sold. If the car I have is 10 years old, have driven like 12,000 miles, I guess. And the type is LE. I forgot what's the meaning of that, but non-dealer losses cylinder. Once you do that, what you do is you figure out that the 5 model would give 5 different prediction. Okay, this is the mean prediction. And as we said, we pick the model 5. In that case, this might be the price I'm going to sell, right? It's a middle price. But I'm expecting what price actually I can sell will be within this range at the end of the day, right? Because this is the 95% prediction interval, right? But this is the best price I'm going to get. So this is how we do it. Okay, we have converted this data into series. Okay, this is dictionary. In the repeated series, I convert it to a series, and I do the data frame to convert to the data structure, and I call it new, and I need to transpose it. DOTE transpose is just flip it. Once I do this, I want to get the prediction for every single model. Okay, so that's why I loop. And here I use the for loop, which probably also learned in the class, is a very special type of for loop that exists in the Python. Is used enumerate. Okay, and actually loop over all this, but when you enumerate, you get another extra counting variable I, which start from 0, 1, 2, 3 up to the number you have 5. So you will run over 0, 1, 2, 3, 4. Okay. So basically what we do is run the regression and with prediction based on the data you got. Okay. And I use alpha 5%, so I need 95% interval and predict that. Okay. And the prediction, I create a new column, okay, which is called model number 1 because you start from 0, the model 0. And once you did that, right, you append this thing, add together to this one, right? So you just have a list of your prediction. And once you do that, because they said they are lists of data frame, so you need to do concat to combine all the data frame together. Okay. So you may wonder whether you can write this by yourself. Don't worry. This is something that you just copy and paste, right? Because no one is going to invent the wheel again, right? So there's nothing. This code is just copy and put in your code. It's done, right? There's nothing to engineer. But I just tell you the reason why you are doing that, right? Because no one is going to change anything, right? Because this is the standard for every single thing you're doing. So that is what you do, right? As I said, this is a model. This is standard error, the mean standard error, and also the observation is the prediction interval. Right? This is estimating the mean upper bound, lower bound. This is individual observation upper bound, lower bound. Okay. So these are the numbers. You notice that I don't have 5 here because I just skip. So this is a 5 model, right? 5 model, yeah. Okay. So we have 5 model, as we said. How can we pick? And always that the trade-off, remember, bias versus variance. And also we want to establish what we call external validity. Okay. Because if you fit the model using all the data, the complex model will fit very well. But you also very often will fail badly when you look at new data. So that's why we use a technique called validation or k-fold validation not to train the model based on all the data. You keep some data there for testing purpose. You train based on part of data. Then you pretend some part of data is going to be test. Probably you learn it from your machine learning class already, right? So I just then I can go very fast. Okay. So this is the model, right? As we can see, right? So the more complex model, if you look at data itself, it will be better. But when you fit the live data, you will not fit very well. So that means that the optimal point here, right? It's like the Goldilocks, right? Not too small, not too big. Medium is good. So as we can see, how to look at this is look at R square. We've done that already. MS, we've done that already. Log loss, also we can do that. And the method we do just R square, AIC, BIC, which also can be done. Okay. And here is the direct method. And in direct method is what we just said. You cut the data into two parts. One's used for training, one's used for evaluate. Okay. You kind of avoid overfit problem. Okay. And to do so, there will be two ways, as I said, validation and cross-validation. I think you learned it in machine learning, so I just try to be quicker as possible. So later we will show that according to different criteria, you pick different model. But let me show it to you. Okay. So what we're going to do is to get the RMSE. So what we do is we'll use this step model .tools.evaluate underscore measures input RMSE. So this function allows us when you give y hat and you give y, which is list of y and list of y, you carry RMSE, right? Which is what? You take the difference between each value, square, sum of them, divided by n, and then take square root. So there's nothing very deep there. Okay. But that will calculate the MSE. And you do it for every equation. What I do, the first one is I get what's the y there. There's the, because on the string, I want to get the snail before the snail. So I strip out, so I split and I get the first item. And I strip because I take away the empty space. Okay. So what y left is just the variable there. And I feed the model and I get the data y, right? So that's why I need the y there. And the output is rather simple, right? You get how many coefficients you're using. It's called the df of the model. Okay. The model dot the model. And you plus one because you have the constant term in the set. And our MSE, R square, is R square adjust. And BIC, AIC. And then you combine them, okay? And then you convert them into the data frame. That is what you get, okay? And here the model is, you can look at RMSE. If you look at RMSE, which one you pick? Model 5, right? If you R square, you would pick the last guy. If you pick R square adjust, also pick this guy. And if you look at BIC and AIC, you would look at the one that is smallest in terms of BIC, AIC. And in this case, you pick the model 3 or model 4, right? So that would be the one you pick. But they are so similar, probably it's okay which one you're going to pick. Yes. Next question. Oh, okay. So sorry. This would be 5. Yeah, this would be 5. No, this would be 5. Sorry, this would be 5. Oh, this is right. Yeah. And we said we really don't want to use the whole model to train it because it will fail very badly when actually take this into practice. So what we're going to do is to split the data. Usually you split it like 70%, 30%. You can do X2 or 50-50 is also okay. But usually you want to use more data to train. Okay. That means that you randomly pick the data. Okay. And we will use RMSE or BIC. Of course, you can use R square as well. Okay. So the method to use is very easy. You just use skip-learn, model selection, import, train test split. Okay. You allow us to divide them into the data, your data here. Use this function. You tell them how large is the train size. Then he will randomly pick. Okay, this random stays your choice. You can put a number there. Okay, you can initiate with 123, whatever. I think people pick 42 is the meaning of 42, right? If you know the mean is 42 is what is I think what's the meaning of universe? That is 42. I think the hacker skies of to the galaxy, an oval is 42 is some special meaning. But anyway, whatever. What we do is you split data. 70% of data is in the DF train, 30% in the DS test. We'll use the train data to run the regression, test the data to run the RMSE, okay, or calculate BIC, all the metrics. So again, we will import the evaluation measure for RMSE. Okay. And validation, we start from empty. So nothing new here. We do the loop over all the models. And I equation. You get what's Y there. Okay. But look at the equation. You take what is before the snail. Okay. And you take out the empty space. And then you run the regression model based on the equation you get using the train data. So the only new thing is this is underscore train is the new. Okay, compared to the previous page, the only difference is your train here, your test here, the test here. Okay, because there's no difference for regression. It's just like you just limit what you train based on train data. Okay, and when you RMSE, you predict based on the text data and check the text data. So there is nothing very new here, right? Once you did that, do the same evaluation. You should see the following. Okay. RMSE turnout is not the lowest model 5, but now model 3. The R square is still the model 5, but BIC become model 2, and AIC is model 5. Okay. So of course, it still doesn't give you a uniform answer. Which to pick is your choice or your boss choice. Your boss will tell you they want BIC, AIC, or RMSE or R square, right? So that means that whatever you want, there's some way to justify. Okay, that's standard statistics, but it's your call which one to do. Okay, it's hard to. There's no way to tell you which criteria better than one over the other. Okay, but when you're on regression, sometimes people do the R square is the thing that people do. But when you don't have regression, right? When you learn the logistic regression or other, then you don't have R square, right? In that case, probably this is not, you don't do it, but probably just simply focus on RMSE, right? There's something that doable, comparable across different type of machine learning code, right? Because BIC, AIC doesn't mean too much when you talk about say random forest or other complicated machine learning code because they have a lot of parameter there. Okay, so at the end of the day, probably RMSE is the only thing that you can compare across different type model. So that means that if I have to do anything that compare across different type of technique, then I will use RMSE. Okay, so now let us get to, I think, the one that you will use for your assignment. Okay, this last two questions in the assignment, we call this, is called the cost validation, which basically we stop here last class. So what you're going to do is the following. We'll do a 5-fold cross validation. What does that mean? It means that I will cut the data into 5 different ways. Okay. In the first way, I reserve the last part, okay, to be test set, and set 2, I have some different location. Of course, these are randomly found. Okay. And what we're going to do is for each set, okay, you will run different model. Different model end up with different MSE. Okay. And then because you have 5 different ways to calculate the model, you will calculate average MSE for each model, and you compare based on that. Okay. And what does that mean? Actually, it's very similar to the bootstrapping. Actually, we create 5 different universe, and different universe, we pretend to do the validation, right? And you average over different universe. So that is very similar to bootstrapping idea. Okay. And let's look at the application, and at the end we pick model 3. Okay. So it's same as the one that we expect to pick. Okay. So let's try. So here, the only new thing, this is, we just learned last class, and also we learn again today, is RMSE coming from this first line, right? And second line is something that new. It's called K-flow. It's trying to ask you to take out, right? How many times you take out, okay? And we learn K is 5, which means that every time we'll keep 20% of data, okay? And since we keep 20%, so there will be 5 different 20%, right? If you use 10 K-fold, that means that every time you keep 10%, you'll create 10 different universe. Okay, but 5, I think, is people way often use 5, but feel free to use 10 or 100 if you want. If you have a lot of data, can be, right? But I think 5 or 10 will be a fairly reasonable number. We set the CV to store our data. Okay, so it's not something very difficult, because you see the code is very simple. Okay, we do a loop over that. Okay, and again, y will be the one that look at the y variable. Here is the main thing here. Okay, so what we do is use the K-flow. Okay, and we would say number or split will be the M.Phil, which we define to be 5. Okay, and shuffle means that once you do it, whether we shuffle the data again, and the way we impose is not shuffling. So we keep the data, randomly pick 20% for the first round. Second round, I do 20% again. So I don't shuffle. So it means that I would not be having problem over there. Okay, because I 20% here, 20% here. So I'm not shuffling every time. And random state is none, you can put 42, right? If I put 42, then you do the same thing again, right? Up to you whether you want random state. Okay. If you don't put it, then you will be depend on the computer CPU clock. what you get. Okay. And this RMC test. So here is the main thing is the first one. Okay. The K-split, clay-dot split, okay, which is defined here, the K-flow, okay, is basically what? It's just the which observation to pick. Okay? And they will tell us, okay, the train index or the tax index in this, which means that they will tell us which row is train, which row is a test. Okay. For K-flow means that we have 5 different set of those. Okay. Say. So that's why what we do is every time we have 5 different type of this thing. First time we'll pick the row ILCs. I means each row, which row to pick, is based on the index redraw. Okay. This set of index is train data. Maybe he picked line number 1, line number 10, number 11, number 12. We will train. And the test data will be telling you another thing. Okay. So maybe the first thing, maybe if you look at this, for example, a little bit abstract. So in this case, suppose we have data 100. The train index will be number 1 to number 80. And the test will be 81 to 100. Okay. So that means that if I do this, I will take a data number 1 to 80 in the train. Row 81 to 100 will be in the test. Okay. So that is what it's doing. Is that clear? Okay. This universe one, this is how you pick. Once you pick, you just run the regression based on the train data. And you evaluate the RMSE based on the test data. Okay. And then you append it to the test result. Okay. And do note that this is only the test RMSE, not the. Okay. And you do this for 5 different universe. Once the loop is over, you calculate the mean. Is that clear? So that exactly we said here, right? So for each one, you pick this data. This will be the training data, this test data. You run for all the model. You loop over everything. This is for loop is doing, right? And then you calculate this. Okay. So remember, this is overall loop over every model. Okay. Within each model, I run this. Okay. So what I run in this Python code is I run through this. And I run this and I run that. I run model by model. Okay. Of course, you can run this loop also fine. Depends on which one you like, but I look all over this. Okay. Because you can reverse the order of this and this, right? You can loop this first and loop the other one. Also okay. But I think I loop over the equation first. Okay. Then the model I have, right, for each data, I can calculate the average RMSE, right? And here, I would have a little bit more complicated is I have to combine the string flow with the number and append there. So this part is simply trying to make the code nicer because I want to export in this way. Okay, so this part is simply that I want to make them look good because I want this flow 1, 2, 3, 4, 5. I want to export this, so that's why I zip over there. So that's make the thing looks clearer. Okay, but at the end of the day, it's not important, right? More important is this guy. Okay, so if you don't want to care about how each outcome looks like, you can simply end the output. It's here, and you're done. Right? This part is not very relevant. This part is relevant because you probably want to see how each universe the model perform. Okay, but at the end of the day, you pick model 3 because model 3 is lowest on average, and also in every single case, it seems it's okay. Right? This case a little bit higher, but overall this is good. Okay, so that's how you pick according to this k-fold validation. Okay. So at the end, this is the result. Turn out as we expect. Model 5 is most complicated, doesn't win. If you use a full sample R square, model 5 wins. But if you use a validation based on RMS, your BIC model 3 wins. AIC model 5 win, but you use the k-fold cross validation, model 3 wins. And if you ask which one to do, of course, you use the k-fold validation, which is the standard, I think, in most of machine learning textbook. So if you ask me what to pick, model 3. Okay. But why we talk about all this? Because once you learn this and you understand what's going on, right? So this slowly progress on how you would do. Okay. Is that okay? Of course, don't worry, you have time to work on your assignment. Then you will re-practice on how to work on it. But if you have any question, feel free to stop me because I noticed some of you already feel very bored because I think this is covered in the machine learning class. So I try to be quick as possible, not to make it too boring. Okay. And very last line, I think that is something I want to say before the break, is you should be very careful when we do the prediction. We should be careful not to just simply run regression. Our domain knowledge is very important. Okay, and this would tell us which variable you should put in the universe of the predictor you want to use. Okay, and I think there's one famous paper trying to answer the following question. Is in the 1950s, someone answered the question: chicken or egg, which go first? And there's a famous paper trying to predict, looking at time series model, where the chicken, look at the chicken production, look at egg production, and whether chicken predict egg or egg predict chicken. And I think the answer was egg predict chicken rather than chicken predict egg. So egg goes first before chicken. Okay, whether it's ridiculous, right? Anyway, but if you lose the prediction, that is what predict, right? But anyway, you should use domain knowledge and know this chicken egg problem will be ridiculous. But anyway, if you want prediction, you can say, right? So you can say how many chicken is there and how many eggs there, right? So you can still predict something. Okay. So I guess I cover how to do this validation. And of course, the code there, something a little bit tricky, but you will copy and paste and learn when you do your assignment. So I guess it's part of the thing is I can't really go through every single slide, but if you do have a question, feel free to ask me during the break. I'll try to help you. Okay. And at the moment, I guess we have you reply, and let's have a 15 minutes break. We will resume later, 15 minutes later.
Yes.
係咯係咯。嗯。So before we start, let's do some trick or treat. 你可以幫到你中意嘅。我話睇你講運氣點嘅。係運氣點快樂。啊？蘭桂坊唔去啦，有小朋友啊。但係去咗開，已經可以開去公園啦。你去蘭桂坊。我話你，學生話你太亂啦，蘭桂坊。你哋開心咪去啦。溝話啦，溝話心機溝女。我想幫同行嘅，有關係。我即係佢我係拉點佢嘅，打抄或者我收2次啦。我呀，可以啦。你聽啊，即係話你上樓咧，我自己嘅，我自己我數埋，新買即係我屋企做多個俾大家。啲人又話，但我唔用得成個So I hope you will be enjoying your Halloween tomorrow. I know some of you going to Lang Kai Fong to have fun. So enjoy. When assignment one answer will release, I'll ask the TA to release it once we finish it. I think within 1 or 2 weeks, then she will release the answer. I asked her to release ASAP. Please also explain Lyso. Don't skip, okay? To group project require PPT for presentation, you need not use PPT, right? But maybe one page, or you can give a handout also fine. Or you can just talk also, okay? But remember, you are not only convince me, I only give 1/3 of your grade for presentation, 1/3 given by your classmate, okay? And 1/3 will be your report, right? So that would be, so if you think you can convince people by being very handsome, being very beautiful, that's okay. You can say, yes, I'm done, give me 10, then go back. Then it may work, I don't know. Sleepy. Well, quiz is always optional. So you don't have to take it, right? If you get full mark already from quiz 1, quiz 2, you get 6 points, right? And then there will be some point for your attendance, right? So probably you already, if you attend all the class, probably you are okay, right? Get, I think, majority of the point of that, right? But if you miss some of the class or you worry about things, then you want to get that because there will extra bonus, right? For going quiz 3. What will be the format of final exam? So I would after this class, I will probably upload the sample question, which I can show you what I did last. I think I did it last time already. So this is the exam paper 2 years ago. Okay, the format will be very similar. It will be some multiple choice question. I'll upload later. Some multiple choice question, maybe like 10 multiple choice or 15 or whatever number. And then it will be some Python code, Python output, and some Python question, right? And this regression, I didn't teach logic this year, so I don't have logic. So that's why I didn't put it there, because I want to make the right sample question for you to understand what's going on. But give me some time, I will just do it. And this some LISO is here, and I have that. And this year I don't have regression tree, but this is what I asked last year. So something like this. So, and usually if you understand the lecture more than half, then you should able to answer 80% of that. Okay, it's open book, so no need to too much worry about that. Okay. And you will see indeed from the average point, I think for this test is like 86, 83 to 86. I can't exactly remember. And many of them actually, a lot of them 90 something, and some of them get 50 or 40, because but majority get 90 something of them. Okay. So if you attend classes, you do your own homework, okay, then you shouldn't be an issue. Okay. If you're not copying from someone else, okay, then it should be fine. Because I'm not asked later, I will see you. The thing I ask is very straightforward. So quiz is already more difficult than what I asked in the exam. Of course, yeah, the quiz I give is already more difficult than the exam I usually give. In multiple choice question, right? The long question may be a little bit similar, but I mean, it's not more difficult than what we have. Okay. Chapter 14. Okay. So what I will do is here is it's a summary of prediction model, and I'll talk about LISO here, and also the auto prediction thing. And you already learned it in the machine learning classes. So I would try to jump over the thing that seems to be very introductory. But in the case that you let me know things that I shouldn't skip, I would just slow down a little bit on those. Let me know. So this is the flow chart, actually, what you should do when you do your project or when you handle the data, okay? So first, we'll start with a business question, right? For example, we want to predict Y based on X, right? We predict something based on whatever you have, right? So this is the question. And that means that we have to define what's the Y. Why we define what's the Y? Then because you have to define how to measure the outcome you want to measure, right? Because suppose you want to see whether A/B testing, right? You want to use a new system and you have to have the measurable target, right? Whether it's how many consumers spend on your product, how many people click your website, right? All the metrics have to be measurable. So why is something you want to have that, right? So this is not something easy. To define an appropriate why, of course, it's the boss design, so you don't have to worry too much with the CEO or CFO or the company. They decide what is the why that they care, right? And you have to define what are the data that you would be targeting, what are data you want to do analyze, right? So this is the training and test split, right? And why is engineering, label engineering, we know that the why you would do is you can log the y, you can take exponential to the ratio. Okay, there's a lot of y you can do. And you also do the feature engineering, right? X can take log, can take square form, a lot of things you can do it. And you define loss function. As we said, the loss function is usually square, right? It's mean square error, right? Once you do that, you build different model and you do model selection. We have already shown you just before the break. And you do the prediction and you look at what they are, right? So that is already done there, okay? So what's new in the LISO, which you also learned from that class, is model selection. It's automatic. You choose it, right? Because so far before we learn is how to pick the model, how to pick the regressor is based on, say, validation method or RNS. You have to use human eye to pick. Okay, LISO is automatic picking. Ask the program to pick that for you. Okay, it's a machine picker. Not learning yet, it's machine picking. Okay? Because we still have to specify what is the model. Okay, and if you machine learning, it's basically the model, machine tells you what the model. You just specify what's the algorithm. Then my regression tree, random forest, whatever, right? This is there, and then you pick, right? But you still have to define at the moment what the model is. Okay. So to y, okay, what is predict y, and then you have to decide what to keep, what to take, what to drop. Okay, and that's actually in your assignment to also ask you how to clean your data, and you decide how to transform it, whether you take log or level, or even you have a contest data, whether you transform to 0, 1, or you look at, remember when we do the hotel price, we divide it into different bins, right? Close, far away, right? Freedom bin, then even continuous, you can transform into different bins. So this is very important. And X also very important is when you're missing, whether you drop them or fill them, because when you do machine learning, a lot of data, you're a lot of missing, okay? Unless the data is from the database. And whether what kind of fundamental form, whether you get a square, whether a cubic term, whether you need to interact different variable. And so it's very important, although we didn't say it out. And because you didn't want machine learning, so we require human learning. So domain knowledge is important to get the model, because you define what kind of model you want, right? Whether you want a square, whether you want a cubic term, whether you want those kind of stuff, it depends on domain knowledge. Okay, domain knowledge means how well you know the data, how well you know how things are related. Of course, also come from theory. And also look at the EDA, right? And that's why assignment asks you to do some non-parametric regression scatter plot. Then you see whether you need a square term or not. Okay. And also we learn before the break, right? We do validation, cost validation, right? To estimate based on the data, evaluate. And at the end, we do the YY hat plot. We do it last time already. So we do it once again here. So that's what we do. The data we have the test set. We have training test, we have test set. Okay, this original data. And once you run this, then you run to the live data, which is something that actual in the production. Okay, so that's how they call the name. Okay, and whether you use level or log on Y. Okay, so I want to skip this part, but just very briefly, when I take log of Y, it means that you're not predicting Y, you're predicting percentage change of Y. And there's some complication. When you take the log, you have to get kind of adjustment, but I don't want to bother you with this, okay? But at least you will know whether your model is predicting change in Y or percentage change in Y. Okay? So that is something that is important in that sense. So go back the car model, which we studied. And if you run the regression, you will see the lot price will fit better, which we will show. But the problem is we are not interested in lot price, which is in price itself. So that's why we would be very careful. Okay. And later you will see they give the same, very similar point estimate. But once you convert into the log, they will give a wider PI because log, although symmetric, you take log is nonlinear. So you will be non-symmetric when you do the interval. So that's why you have to be very careful. Usually you care the price, so probably you will still keep the price rather than not price. Okay. But so that's the data, right? Because the price in H is nonlinear, right? Then if you fit, this is okay. If you Y is nonlinear because you fit H square, okay? H and H square. And you take log, you also fit H and H square, and seem to be a little bit better, right? And seems to be okay. And if you look at the textbook, they will tell you that the prediction interval is larger in the log model. So in that case, if you want more accurate prediction, you would lose the price, not the log price. Okay, so something to keep in mind. So as I said, this part, the main thing is to look at LISO. Okay, what's a LISO? The name suggests is least absolute shrinkage selection operator. So that means what? It's automatically selecting the regression through least absolute shrinkage, which you see the absolute term over there. Least mean the minimize. Absolute is because absolute minimize absolute, not the square. So basically, you can see this is the probably you would say the very beginning of machine learning. It's the machine to learn which to pick. You just input all the regressors there. Machine pick the one that fit the best. So, and there's no domain knowledge. Okay? And that's basically is a regression with a modification to reduce number of variables. Okay. And why is the case? Because Why this would fit is because usually IT data, a lot of variables are highly correlated, okay? And you don't know which one to pick. Then this is fit very well, expert IT data, right? Because you look at the website data, right? You will see how much time he spent on this page, when he clicked this button, and how much time his mouse in which area, and so on and so forth, right? And all these are highly correlated, okay? And in that case, you pretty want to keep one of those to do the prediction, right? Because they are also related. Running standard regression will not work very well. And you just want to keep limited number of them, because we look at the data, there will huge number of columns, because you keep track of everything they do, right? How many times they click nonsense, right? If they use the screen, how many times they scroll, they keep a lot of stuff. And because of machine learning, you will see one thing we call hyperparameter, which is decide how machine learn. In this case, it's called alpha, which you will see is control how the shrinkage work. Okay? So this is LISO, but we will soon see the model. This page. So multiple regression is y explained by x. So it's fitting a plane, if you remember, right? The plane. And you minimize the vertical distance between data and the plane, right? And this is what we do when ORS, right? Least square, right? This is a model and y, and you can reverse it. I think the usually I write this is okay, right? The data minus the prediction, or sometimes we write prediction minus y is the same because square. So what's new here? LISO is this part is same as before, right? This part is same as this guy. Nothing new, right? This is regression. What's new with this part? Okay. This is absolute shrinkage, absolute value. Okay. You put the coefficient here. Okay. And you try to minimize this beta. Okay. And you look at absolute value. What is doing? What is doing? Because you want to minimize this, right? So it means that if some coefficient have high positive, high negative, they don't like it, right? Because as I said, many IT data, many columns are highly related, right? If you want to fit this kind of model, sometimes will be you're positive in one column, high negative in one column, that fit very well. Okay, so that's LISO will calc this out. If something positive negative, actually they force them to be close to zero, right? Maybe force one to zero, and one the coefficient much smaller. Okay, so that is how this thing works. Let me repeat what it works. Is to make the regression, standard regression, right? But you're trying to minimize the absolute size of this coefficient, right? Absolute size. So if coefficients are highly related, right? It can be best fit by having positive in one coefficient, negative in other, right? But they are redundant, right? Maybe one redundant. So basically, you want to shrink it to some of them are zero. Okay, you don't need them. You probably drop one them out of the order. So usually, what we do is basically if one positive negative, we probably just keep one of them. Okay, and then the coefficient will become much smaller. So that is the main idea of why this would work. Is that okay? Is that okay? I think you learned it from other class, but that is what the LISO does. Is that okay? Or still want me to explain it further? So the idea is that right, imagine that you run this is y, this is x1, this is x2, right? And maybe So this is y, this is x1, x2, right? Regression is trying to minimize the vertical distance, right? And the beta coefficient is trying to decide how flat or rotated it is. Okay. And of course, the more different slope, right, represent the higher slope you get, you have much higher betas, right? If flat actually doesn't mean, if flat doesn't mean it doesn't vary, right? Just like if 2-dimension, if flat, the beta will be 0, right? So it's trying to force it to flatter. That is what the LISO is doing, okay? And it would prefer, in the case that try to make it as small as possible, okay? Because of you minimizing the absolute, right? So you punish by looking at the triangle, right? The more out, you get more punishment. So they try to fit in a parallel, the closer to the center, the better. Okay, so this is the same. So if you fit the plane upper and upper and upper, you punish. So if alpha is large, so you want to shrink this as close as possible. So that's how this thing looks like. Okay, because you add a term of this plane. So you minimize the loss and also this plane. The further away, you get more punishment. Okay. So that is the main idea. If you imagine, just look at the linear regression, maybe easier to think. Okay. So this is the point, okay, and the fit line there, okay, which is y equal to beta 0 plus beta 1 x, right? Or as implied that you want to minimize this square, okay? And LISO would say, look at the LISO, you want to minimize not the slope, but just the coefficient, right? So what it's doing is, if you would have quad beta alpha, okay? So that means that if you increase the beta, okay, you're punished by alpha, right? So that means that once you add all this, sum of square error, you would also add the slope, which is beta, okay, and times alpha is your punishment, okay? So that means that you want to reduce this. Of course, you will not as fit as before, but you reduce punishment. So you try to make it flat, okay? So if you pick alpha very large, for sure, you pick a fixed line, right? Suppose I pick alpha is as large as I want, it will for sure a flat line, right? Because no matter how good it is, because the punishment is so large, you always want to make it flat to avoid the punishment, right? So same go for 2-dimension, the plane there, okay? You want to make it as flat as possible, okay? And the way that, because you care absolute value, so you try to reduce thing to 0 as much as possible. That's the idea behind. You don't care about negative positive, you want to bring it to 0. Is that clear? So okay, I think 1 dimension is easy to see, right? Because you fit this, you punish this, so that's why even though there's a best fit, you won't do this. You want to slightly reduce this, less fat, right? then you reduce the punishment, right? Because you punish having a slope. Okay, that's why you want a simple model. Okay, because you have multi. That is why how you get the model simpler. Okay, is that clear? Because if alpha is like 1 billion, then beta will be 0 because you don't want any punishment. If alpha is very small, you just slightly adjust a little bit, right? You just reduce a little bit slope. Is that clear? That's what LISO does. But of course, when 2 dimension is the same thing, right? You just make it as flat as possible. Okay, just the 2 dimension, right? Is you want to try this x1, x2, this y. You try to make it flat, and maybe this you want to make it flat. Is that okay? I hope it's okay. But if you're not okay, then just remember the intuition, right? Because you minimize this. So you want to make this as close to 0 as possible. So when you run LISO, I think other class will tell you, some of you ask me as well, because the way that you minimize this guy, so you want to make sure that no variable has very large x, okay? Because if you multiply x by 2, the beta will be reduced by half, right? So you scale up or scale down will be an issue. And the mean will also affect the beta, right? So that's why you always what we call normalized variable, right? So you just normalize, you minus the mean over the SD. So everything has 0 mean and SD. And the Python is very easy. Just 1 line code, scalar, and then you're done. Okay. So later you see. Okay. So that's how we run LISO. Not very complicated. So here we use the stat model API. And we use the skitlearn linear model LISO. And we use the skitlearn preprocessing standard scalar. This is to get it to mean 0, variance, or standard deviation 1. And what we're going to do is, this is data. And I use the standard scalar. Okay. And I use the scalar dot fit transform x. I call x scale, which means that everything, I run this 2 line, everything will become mean 0, SD1. And I do LISO. The alpha is hyperparameter we said, and you fit it, and just you fit the answer. So this is how we run LISO. Okay, there's nothing deep here, right? Just because if you forget about the scale, just LISO alpha 1 dot fit, you're done, right? This is just to handle the data, right? So only realize this line, right? These 2 are just to feed the data into 0, 1. Okay, just very simple. Okay, and here is LISO. Very often you would plot a graph, look at the coefficient. That's what I do. I do a bar chart and I rotate it, and it will show by LISO. You can see x1 and x3 become 0. Okay, I do x2 is done. So by construction, I will try to the effect of very simply adding a absolute term with shrink something to 0. And of course, one question is how to get the alpha, right? What's appropriate alpha? Because alpha, if big, everything becomes 0, right? Alpha is small, nothing can be done, right? But what is alpha? What should be the hyperparameter? And probably you studied the machine learning class, you can tell me, right? You would use K4 validation to optimize the hyperparameter. So you would try different hyperparameter and one K-fold validation and figure the best alpha. Under this alpha, you run this RMSE. Under this alpha, you run this and figure the best alpha. That's how we do. Okay. 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 So what we do after the break, we will do into Airbnb data. And the question is again very simple. You have an apartment to rent, which probably not okay in Hong Kong because it's illegal to do Airbnb. But suppose you have Airbnb, you have a summer house in somewhere else, right? And you want to rent out. And this is the data from inside Airbnb. I think it's some website that describes the Airbnb data. You have many observations, but importantly, you have 94 variables. So that is the reason why you need LISO. And you will see the key variable. This is from domain knowledge. Why? Because the rent should depend on the size of the house, apartment. What type is a house, or apartment, landed property, castle, right? Can be anything. But actually, castle is an Airbnb. The data I think is there, but I think they will exclude it, right? And location, where it is, amenity, right? How many toilet you have, how many bedroom you have, right? And you predict the price because you want to say what price to rent out your free house. Okay, so we'll do this after break. Let's a break of 15 minutes. Since it okay, yeah, that's okay. Let's a break 15 minutes.係啊係啊，我哋個唔係
就係講令到個 beta。當你 introduce 咗個 alpha 之後，個 beta
alpha 係你決定嘅。
話係你我哋用呢個嘢去 set。
係冇錯，係最好嘅 alpha 係點揾出嚟？點樣？係你嘅試嘅唔係咁樣，你唔會 adjust 呢個 alpha，你係用 table validation 去揾最好嘅 alpha。你個 maximization 唔係清楚。
個 minimization 係不停 change 個 alpha 到之後，
唔係，你個 alpha adjustment 係 based on RMS。你知唔同嘅情況之下 ，RMS 你實幾落嘅。你 train 個 model alpha， 但係你個 alpha 呢份 alpha 你 minimize 嗰陣時就會 minimize 個 beta， 但係個 alpha 點樣決定咧？就係佢 train 出嚟。啊？我不嬲啦，我兩堂咩？佢講。
點解有啲 variable 要 take long？哦，因為佢 non-linear，
即係好似
即係你如果 data 係咁嘅，你覺得佢嗰個 data 即係嗰啲價碼需要逐少個咩？記得啊？要食咁就知道佢係而家會你記得你呢個係係你呢度佢直接咁玩家入去咩？因為你講緊 underlying model， 你必須我哋可以咁你覺得佢係直線，覺得佢明線性。如果唔係線性講，你非線性嗰陣時，就非線性。你有冇搞笑可以搞到複雜㗎？ 炒廿分鐘咧，我哋先炒嗰炒。咁嚟得，我哋嗰年嗰時我從四邊四個上，加咗啱比大，比之後車度咧，咁所以佢收唔俾佢。你知唔知我心抱？係啊，你嗰個時代，你嗰個時代有一樣嘢。係，我話我知道啦。係快樂自己決定。係，我先話係咪嘅？因為我真係唔係幾多時。即係啱埋嗰陣時，真係快樂嘅全部都有話。啱我大嗰陣時，我喺度跟住嘢。特別康嗰個係真係嘢。之後哇，我有直播有先我停咗啦，因為你都係你我係唔使嘅咁，佢而家唔知道時嗰非常之點。喂，如果你冇呢嚿嘢嗰陣時，咁啊正常不成。咁但係如果 alpha 你係要一路咁大嚿落去，咁你唔通有程度一路咁攀住數，一路 alpha 一路咁。係撈埋喺個玩可以咁樣講，就今晚你今晚你係翻嚟睇到你好想有多玩幾條。加上咧，即係話其實佢哋即係其實最想做嘅就係史無其事，因為盡量點樣發現到俾佢上咗，係最關鍵嘅就係話，哇唔係啊，唔係你想炒，你想炒，真係炒飛，真係炒，我未啊，我想。啱啱嗰啲我哋可能邊個先係我哋唔知道。如果佢我係嗰啲 X 你係拉住我哋識兩蚊因為某時唔想諗，所以翻嚟上夾硬屈你咁。因為你要食出嚟嘅啲10分，自己嗰度自己選擇，咁自己講自己。因為個英文喺呢度講咧，所以alpha 你覺得我有三次嘅？我識得三味嘅嗰啲嘢，係咯。七毛。但係我分別咗歐文嗰陣時，我俾我今日集條世界，即係你要錄歐文嚟。啊，今日集標先歐文大咯，其實係即係呢一集邊即係呢一邊嘅情況，呢啲叫做唔會咯，呢啲大家呢個翻嚟嘅。所以你直線咁嘛，你啱啱嘅直線。我話你收嚟都決定就係呢個一樣，所以我哋
So, let's return. So, we'll illustrate the idea. Okay. So before we do, because many people ask me the LISO. Again, I'm explaining again this diagram. Again, let's consider one variable regression. The idea is same extend to more than one variable. So remember the regression, what you're doing. Regression is minimize the sum of square distance, right? So basically you are looking at each data point. You minimize this distance, right? Okay. And this is the case when alpha equal to 0, right? So you would just care about the distance to the line, and minimize will be your beta, right? When alpha equals 0. But now consider case alpha is some small number. What you're going to do is you will still minimize this, but you will get punished by alpha plus. So you the MSE, right? Or the SSE, right? Will be the SSE, right? Plus this guy, right? So by construction, usually you would have a much fatter line because you're punishing the beta, right? So you want beta closer to 0 as possible, right? You don't want because you get punishment. So beta will be less than what you get when alpha is 0. So alpha and the beta will be inversely related, right? The higher the alpha, the smaller the beta, right? If you keep increasing the alpha, beta will eventually go to 0 because you punish for every positive coefficient, right? And punishment so large, then you just that line. Okay, so that is what it is, right? And in general, right, you're minimizing this SSE, okay, plus alpha plus absolute beta 1 plus absolute value beta 2 and so on and so forth, right? So that is what it means, right? So that means that you would try to look at the coefficient or the slope. You want to reduce it as much as possible, right? So in case of two-dimensional world, vertical is y, this x, right? If you look at the ordinary regression, ORS, you just minimize SSE, right? Look at the point and the plane, try to minimize the distance, vertical sum of square distance, right? But once you increase alpha, you would try to make it flat, okay? And if you keep increasing alpha at the end, you become a horizontal plane, okay? Doesn't change with the y, right? So that's the idea, right? So just alpha and the coefficient are inverse correlated. The higher the alpha, the lower the beta. And remember, the alpha is given, okay? You give this, I do the minimization. But the question, of course, is beside your boss or your client, how can you decide alpha? And the alpha is designed through the what we call K-fold validation. which means that you produce many universe and look at different alphas, which alpha give you the best mean square error, right? Or the sum of square error, whatever you, or MSR, right? That one with the best alpha, we'll use it in production. Okay? That is the way that we will do. Okay, and we will show you how to do the code. It's very simple. It's called LISO CV, and just one line code, and you do it automatically. Do all this. We'll go over that. Okay. As I said, LISO shouldn't be something I talk about, but since you don't want me to skip, so I just skip it because I assume you know LISO already. So but in case you don't know, I can still feel free to ask me. And if you still don't get it, ask our TA. So you're happy to answer your question. Okay. Or you can just email me. I can try to help you. If a lot of people ask the same question, I'll record a video, try to answer them as well. So this Airbnb data, I'm not going to run it because I think the code is already there, but I just explain line by line to save time. So NumPy, Panda, URL, Panda read, and describe is something you know very well. Okay, I'm not going to do that. And here, have a lot of missing data. So you have to either ignore it or you feed from other value. So here, a lot of missing data, no prices, you just can skip. And say many unimportant variables kinning free and how fast the host responds. This is data that probably doesn't affect the price. Okay. And also, sometimes you have number of beds in the room, but sometimes you don't. So they're missing. So you can just, if you miss it, usually you can fit it from how many people can live there, right? So usually 1 people, 1 bed, right? So if 5 people can live there, so if with the number of bed, you can say 5. So that is how you can do it. Okay, missing doesn't mean that you have to drop the data. Sometimes you can fill the data in. Okay, so this is checking missing. So it's checking whether it's null. Some of the data check whether each variable is bigger than 0. So check the missing data. And here I will drop price. If any, I will drop them. And here, as I said, if number of beds is missing, you fill the NA using how many people we can stay, number of accommodations. And here is you drop a column, which is cleaning fees, okay, and host response rate. This is how you drop. SS1, you do the df dot drop, okay. This is how you drop columns. Okay. Actually, you can just ignore it because one regression you don't have to run this one, but doing this term can reduce the size of the data, and can make the regression faster. Okay, but otherwise, I mean, if your machine is fast enough, you can ignore this. Okay, and here, as we see, we do the grouping. Is number of rooms, bathroom. You would say 0 to 1, 1 to 2, and 2 to infinity. Why? Because more than 2, which pop usually doesn't really matter anyway, right? And 0 and 1 are different, right? So there's basically it's just 0, 1, 2, and more. 3 groups. And here is there are data like how many days since someone write the review, and what is the review score, what are review score per month. Some of them are missing. So what we're going to do is, if they're missing, what you do is fill the median. Okay, you don't know what to do, fill the median, but with flats, which means that we will have a dummy variable, which is saying there's 1 if you fill them. Okay, so we fill them with flat. So this is also a standard technique when there's a gone. You will see when I do the code. Okay, this is what I do. When you have bathroom, if they're missing, okay, you would fill the NA through the median. Okay, and when it less than 1, because 0. When it says more than 1 and less than 2, call it 1. And more than 2, you got 2. That was the case. I think that's typo here. You should have no equal sign here. You should have equal sign here. Sorry. You don't have equal sign. You have equal sign here. Sorry for that. And here is I would try to look at the case where the data has missing. Okay, I would create a flat which is 0, 1, such that if they're missing, or the loop here, loop over everything, and such that if they're missing, I put it 1. Okay, and once I do that, I will fill the NA with the median. So this is the code that I'm cleaning data. Okay, and then I will also clean number of review from 0, 1 to 50 and 51 or more. Okay, and how I do that? I think the author of this book, they said they do the scatter plot and look at this 0 to 1 have 1 group, and 1 to 51 1 group, and 51 onward. So that's how they do it. So basically coming from EDA, they run a scatter plot. So that is something simple, right? Less than 1, you call it 0, and 151, you call it 1, and so 151 more, then you put 2. Okay. Now, once we clean data, we can run regression, right? So, so here, we have number of people. Okay. You would also do the square. Okay. Because I think if you are much larger, the prices go up quickly, right? And number of beds, and you depend on apartment or house, and whether the room is entire apartment or just part of the apartment, and how long have been reviewed. Okay, so this is the model. Okay. So here we have some basic model that we share by all the specification. And why we need them? Because these are coming from domain knowledge. We believe that the price of the rental would depend on how many people you can live there, how many beds you can this in the room, what the type of the property, what kind of room is shared, how many things have been reviewed, and whether this apartment have been reviewed or not. Okay. So here you see why you have to divide by type, because if you own, depend on your private room or share room or the whole apartment, the price are different, right? So that means that you have to include them into your regression. And as we said, number of common day and number since review, we do a cubic or square term there. So here is the model we have, right? So basic add will be basic model plus bathroom, how the cancellation policy, bed type, and the review, there's a review score, and whether they're flat, they're missing. And there will be polynomial, which is square and cubic terms. Okay. And here we use something, what we call regular expression. Okay. Why we do that? Because the 94 variable. Okay. So the data would do is some anonymity. The data would be called D underscore. What's D? This is a dummy. So a bunch of CO1. Okay. In all the data. CO1 may be something like whether we have bathroom, whether your window, whether allow cats, whether pet property, those kind of stuff. Okay, whether heater, whether air conditioning. So this bunch of D. So this is a way to get the thing that start with D and end with anything else. Okay. So I'm not going to explain this regular expression, but that is how this being done. And here you will see whether you have cats or dogs, whether you have TV, okay, can change the price a lot. Okay, cancellation policy. So that's why you would do the interaction. And that is also, you can see the number of people and price are non-linear. So that's why it's not linear line. You put a square term and keep a term there. Okay. So now we go to the end of our specification. So very long thing. So X1 would be the room type. Okay. This is why you get this multiplication coming from this kind of model. You will see they are not linear. So that's why you multiply all this with the cats or dogs, air conditioning, okay, and all this crazy thing there. Okay. You can see even LISO is not just ask the computer to pick many, because there are 94, right? There are many. If you ask the computer to do it, then still the computer will crash because there's too many things to do, right? Because 94, there are many ways to interact. So you still have to make your own judgment from the data to decide what to interact. Okay. So there's still, although the machine do many things, but as humans still have to do something. Of course, you learn machine learning. If you don't run random forest, you can just throw everything there, then you come out with a backhoe and come up something back. It's fine. But LISO, you still have to do this thing. Okay. And if you run random forest, it's actually in the background doing something in the background, or the calculate for you. So you don't have to worry about those. But LISO, you still have to worry about how to pick what kind of things on the pick, right? Because LISO is just automatically select, right? You have to still give him the biggest set, you can select. Okay. And if random forest, you don't have to worry. Just throw a bunch of things, they will pick up whatever interaction, whatever thing, square term, you figure out. But at the moment, we run LISO, we have to do this. Is that okay? So you learn machine learning, you figure out why we do this, right? But LISO, we have to do this. You have to provide the biggest thing you want to consider. And the computer pick the one you like, okay? But you still have to give him the option, A, B, C, D, E, F, G, H, I, J, K, okay? And 94, there are many, right? Many kind of combinations. So you have to decide what to pick, okay? And you will see a huge number because amenity is a lot, right? So you still have a huge number of regressor, okay? Turn out you see we will have 8 different specifications, and you will see the number of coefficients go like crazy. At the end, you have 300 coefficients, right? Can be because interaction, right? Because you have any amenity interact with property types, then you end up very huge. Okay. So the good thing is LISO can tell us if we run this 300 coefficient, which are important, right? Because it's a huge number. So LISO will automatically pick some of them 0, some of them positive, some of them negative, right? And LISO will tell us which is good, right? If you increase alpha, it will be very simple. Okay. Is that okay? So here's the bunch of regression. Okay. As we do, right? Price based on number of common day and price based on basic levels. And we will have a price based on different thing, right? Level 3 will be adding the review, polynomial, and then the x1, x2. x1, x2 are some amenities. And there will be 7 or 8. So it's many things you can combine together. Okay. So what we're going to do is equation, list of 8 models. You loop over this. Okay. So once we've done this, then basically it's same as what we have seen before, right? Once you set up 8 different model, you just run 8 different thing through the LISO. So to fit, as we said, we will do k-fold validation. We'll do the 5-fold. Every time I use 20% data. So our old friend, test string split. We did it before the break. And I tell them I would use 5-fold, so it's 20%. And now I use the RMSE as an evaluator. So that's why I use this tools evaluator measure as a k-fold, as we've seen before. I use the step formula API to run the regression, NumPy to do calculation. I use M.Phil 5. CV will store my RMSE data. So this is something that you have seen before, nothing very deep here. I run over all my 8 equations. I loop over them from 0 to 7, right? Each equation. I grab the y, but actually y in my case is price. So if you don't like this line, because I always run a regression is y is price to basically just price. If you don't like this, because I only do the price, so you can just, you don't like this line, just like this is only y is price. And this is my model. Okay. Why I did that? Okay. So I run the regression. Okay. This is doing the full model. So I looked at full data. I run the OAS. I look at the coefficient. And I calculate the RMSE looking at the full data. This is the RMSE based on the full data set. Okay. And then I do the k-fold validation. I look at the 5 folds. Okay. I do the k there. And I separate the test and train. Okay. Here is, or I do the 5 folds. So for each flow, it's same formula, right? I will look at the data from the test and train. I run the regression based on the train. And I calculate the RMSE based on test data. And once I do it, I append it there. Okay. Then I calculate the average of the test and average of train. Okay. And once I did that, I collect all the outcome, right? RMSE, coefficient, model, R square, BIC, train, and test. Okay. And I just make it look nice. Okay. Combine it from dictionary and then combine. Okay. And then this is the one I create data frame to take out the thing I like. At the end, this is the model I get. Okay, it's the result. Okay, because these are so similar, so I just go a little bit faster. But in case you don't know, you can ask me, I can explain to you the one that you don't know. And you will see R squared, because this is the whole model. Of course, this always increase. And look at the test RMSE, you will see it's not the larger model better, right? Turn out that this is overfit. So this one is better. Okay, this is simpler model. RMSE is lowest. The most complicated one doesn't work very well. And use BIC. I think the best model is this guy, right? The model 4 is better. Okay, but in terms of RMSE, then this is the model 7 is better. Okay, but do note that I don't have LISO here yet. Okay, I only look at non-LISO. Okay, look at different model. Look at that. This is what we have done so far already, right? This we done it in the before the break. Okay, now I think we do LISO. Is that okay up to here? Okay. This is trying to show you the graph using the CV data. You plot the coefficient, right? X the coefficient, Y and train. Why I want to do that? Because I want to show you. Once I draw this, I want to plot the text RMSE and train RMSE, and put a legend, the same thing, because I want to show you this graph. If you look at the train data, right, the more you feed, the RMSE is decreasing. But look at the test data, you drop, but you increase, right? So the best will be somewhere here. So as you say, the model 7 is the best if you don't use LISO, right? Because the complicated model doesn't fit very well. Okay. So now let's do LISO, right? Because that is the reason why the complicated model doesn't work very well, because you have 300 variables and many of them can be crappy, right? So you want to avoid the crappy thing. LISO is the way to go. Okay. And at the beginning, we'll fix the alpha first. Okay. And after that, we'll train the alpha. At the moment, I take alpha 4. You can put whatever value, that doesn't matter. I just put 4. Okay. And I will do the 5-fold validation. Means every time I take 20% of data for tests. And I scale the X first. I scalar means 0, standard 1. And RMSE, I can get lower. Okay, let's see. Remember, LISO is only meaningful when you have large number of regression, right? You only 1 or 2 regression, then probably LISO is not something in your mind, right? So that's why you focus on the most complicated regression. Okay, and to do this LISO, you have to do something we call pass SY. The reason you do that is you increase the speed. Okay. So you would do the data, you separate Y and X. And the feature names are the decided info column names. Is just what it means. Okay, you just look at X. Okay, once you do this, we will do a test training speed. Okay, this is all the X. This is test train. Okay, you have 4 lines, and then this is the test training speed. Okay, because I'm not doing the DF, so that's why I have the 4 column. If I DF, I only have 2 column. Okay? If you give X and Y, then I'll have X and Y train, X and Y test. If I give the data frame, I only have train and test. Okay? So that's why we have 4 elements here. So the reason why we need to do this D matrices because we want to apply this standard scalar. Okay. So we have to use the pre-processing standard scalar, and we scale it because we only scale X, not scale Y. Right? So that's why we just split X and Y. And we scale X, keep the Y the same. So that's why we do the matrix split. And we scale fit transform the train and fit transform the test. Okay. We normalize both training and the test data. Okay. To mean 0, variance 1. Once we did that, we do LISO. Okay. Remember, LISO is scalar linear model LISO. We fit the LISO, use alpha equal to 4. Using our training data, we scaled it because I want to, when we run LISO, we always scale the thing, right? And run the Y. And here is the key part of the thing. Because when you run the LISO, you try to make everything 0. But at the end of the day, you will not be absolute 0. So that's why I would do is I would run the coefficient. I run to 2 decagon places. If not 0, I will call it non-zero. Okay? Let me repeat the statement. Because you run the LISO regression, you will not, many coefficients will be close to 0, but will not be exactly 0. Okay? So decide what you consider 0. In my case, is I would decide that if you run to 2 decagon places, it is still 0. Okay, then I will consider 0. Okay, so that is a little complicated. I could put that frame based on LISO coefficient. I got it from there. I look at feature, look at the coefficient. I will keep them as long as the coefficient run to the 2 decagon places is not equal to 0. I will keep them as called non-low LISO coefficient. And I will run the coefficient to 3 decagon places. So for you, you can just copy the code, right? But the only thing you may want to change is this one, right? How small you want to say consider 0, right? Whether 2 decagon places or 1 decagon places or 4 or 5, depends on your taste, right? And once we did that, we collect them, and we want to draw a horizontal chart, right? And this is the line that you try to draw a bar chart, right? And this X label title, draw a line there, right? It'll be like this. So we see what we kept there will be meaningful, right? Just turn out to be, you don't have many variables, right? Remember how many we start with? 312. Now how many left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So LISO basically strength 300 into how many are there? 13, right? So basically all of them are gone. So you can see the powerful LISO. Of course, I choose alpha is equal to 4. Of course, alpha, if you make it 2, it'll be longer list. Alpha is 1, it will be even longer. I make it 4 so that it is easy to see, right? But of course, you can see maybe alpha is too large, you shrink too much. If you don't like this, you should take alpha smaller. Okay, the bigger the alpha, the shorter this list. Okay, so it is up to you to decide how long it is. It's your alpha is your choice. Okay, and of course, you want to look at this new LISO. What kind of mean square error you get, right? Or RMSE you get, right? So I use the mean square error or RMSE. It's fine. I think I can use RMSE. Why I use this one? I don't know. I think I got mad. I mean, I should just use RMSE. I don't know why I use the mean square error and take a square root. For some reason I'm crazy, but you should use a RMSE. This is fine. Okay. Why I do that? I have no idea. Okay. And I think it's strength to, as I said, it's strength to 38. So that means that if I have model X, I use LISO, it's better than model 7, which is 39 something. Okay. And the question is, can I do better than this? Okay. Sorry, this would be alpha. Okay, because I changed the notation. This will be alpha. Okay. And what I'm going to do is the alpha is from 5.05 to 1. Okay. I mean, can be any number, but I'm going to search it. Okay. Choose the best one based on FIFO cross validation. Okay. So don't worry. Python has a very simple code. You just do this and you're done. So very happily. So you will call the LISO CV. You just tell them, it should be this lambda, which is possible value for alpha. Okay, it's coming from 0.05 to 4. Oh, I see. So this will be 4 here. Sorry, this will be 4 here. 4. Sorry for a typo. And what I do is I do a LISO CV, okay, using the all possible alpha. I use a FIFO validation, random state 42, whatever you like, right? And then I fit the model, okay, based on the train data, scaled it, and the Y train data. Very funny because for the Y data, you have to declare at this thing for this LISO CV to work. Okay. And basically you change the type. I think you change it to the data, you change to the data structure, not the vector, not the list number, but you have to change the data frame. So this is the line that you change it back to the data structure they like. Okay. So that's something, I don't know why they do it, but maybe in the future you don't need that code. Okay. But at the moment you have to surprisingly add this line to make it work. Otherwise, you will see if you don't have this, they'll complain. As far as I run it, okay. But maybe recent code they just allow automatically do it, but who know what? Okay. And later you will see if you able to pick the best model actually cut to 71. Okay. And later you will see a 10% drop in the RMSE. Okay. And you see simple model, you pick model 7. Otherwise, you would do model 8 with LISO. Okay. And the model like this, right? Once you run this, you pick the nice one, pick the non-zero one, right? So at the end, you have 300 of this variable. Okay. But of course, many of them are 0. So 1 is gone, 5 or 6 is gone, only left of 71 data. Okay. And of course, you can look at the top 10 list, right? Look at absolute value, look at the top 10 data. Okay. And you can just plot the data, this top 10 list there. Okay. Then you will see if you run the regression, then these are the important things, right? Well, the bathroom is important, whether your hair dryer is important, with smoke detector, how many people you're there, with the private room, and also this kind of stuff. I'm not going to go into detail. And, and this is the one that I'm going to pick the RMSE for all possible value of alpha, okay, by looking at this flow, okay. Look at the model with RMSE.path, very complicated code. and apply the square root, and then you run over this code. Okay, then you give you for each level of alpha what kind of RMSE. Okay, and that will tell you which one to pick. This is what I said. You run the fivefold validation, pick the best alpha. Okay, and if you do the model alpha, this is the best choice alpha, and you tell you this one. Okay, and this is my answer. Okay, so and since I overrun by 1 minute, I will talk about the wire plot next class. But it just basically just two set of two fewer slides. But I would not take more time than I should. So already 1 minute excess. So enjoy tomorrow Halloween. In case I'm fast here, I will review again tomorrow next class. So enjoy Halloween.